So welcome to the second part of the Q&A session, Internet Protocols in Mobile Communications. And today I will mainly cover the wireless sensor networks, and the TCP mechanisms. Okay, so let's start. Wireless sensor networks. It's not a big topic, but there was a lot of research done on wireless sensor networks. I'd say 2000, 2005 it all started, because at that time we had small integrated microcontrollers with some sensors, so we could scan, monitor the environment and do something. So some actors, switch on, switch off things. We could measure humidity, temperature, etc. We covered the last time mobile ad hoc networks, and the key idea here in sensor networks is we have many more devices. And to be honest, we do not really care about a single device. So if you have 10,000 or more sensors, you do not care if one of these sensors fails. So maybe you just want this average temperature of a certain region. So that's the idea. So the scale is different. We are more, not address-centric, but more, let's say, value-centric. So we want to know a certain value, an average, a median, whatever, of a certain area. So cheap devices. That was the core idea. Okay. And starting from these wireless sensor networks, there was also the term cyber-physical systems, which means, okay, those devices interact with the environment. And then, I'd say 10 years ago, suddenly the term Internet of Things popped up. The term itself is a bit older, as I told you, from 1999. But now we have the Internet of Things, which basically only means we use Internet technology to connect everything. Everyday things, smart homes, healthcare, building automation, agriculture. So there are some nice field trials where really measure humidity every, let's say, 10 meters. And then you can do something that's called precision agriculture. And the core idea is, let's use Internet technology for those many devices. But then I also explained there are some problems if you use Internet protocols in such scenarios. Because if you think back, the Internet, well, it's from the 70s, 80s. No one thought of millions of devices. Everyone thought of, okay, this is a computer, and we have maybe 4 computers connected. That was the start of the ARPANET, 69. And today we have millions or billions of devices. And one of the problem is related then to the classical protocols, IP. And this is exactly the first question, or the second question is related to. So second question was, which problem arises using the classical internet protocols together with, this is one quite prominent example for protocols used in the IoT area, it's Zigbee. Zigbee based on 802.15.4. So, what are the problems? Large overhead. Exactly. Think of IP version 4. You have 32-bit addresses. IP version 6. Wow, 128. So that's quite a lot. And then if you look at all the limitations, exactly what you write, the limitations of the physical layer, we want to have short packets, relatively short packets. We can transmit some bytes and that's it. We cannot even squeeze in the header of IP. So, and if we can squeeze in the header somehow, there's almost no payload left. And now think of what is inside the payload. Inside the payload, we have maybe TCP, UDP, and on top of that, maybe you use HTTP, and then you have the application. So what is left for the real application? Maybe a single byte. And this was exactly the idea of we need different protocols, or we need a layer in between, or a layer that translates from the IoT world into the classical internet world, where we have the normal IP protocol. And this is exactly what we have this 6LoWPAN for. Please, again, you don't have to know all the RFCs, etc., just the key idea. So the problem is we can offer only, well, at least in this example, 33 bytes for applications. That is not much. So 33 bytes. So what can you do with 33 bytes? And then together with this problem, we know that IPv6 requires a certain message size, at least this 1280 byte. So this doesn't really fit together. And that's the problem. And this is why we have protocols like 6LoWPAN. And 6LoWPAN is used then in the context of Internet of Things and wireless sensor networks. Okay, that's just one of the examples. There are also some more protocols we use in this wireless sensor network context. What are the challenges if you think of Internet of Things? Do you know some more of the challenges? You may think of mobile and wireless communications, maybe a bit more, maybe related to security. Can you think of some of the problems? Because I showed you there are so many promising applications, but what are maybe problems? So, no battery life. Battery life is a problem. Firewalling, if I interpret this FW right, then firewalling is not available. If you come up with all kinds of attacks, think of someone attacks the IoT field, well, you have weak devices. Battery life is really a big problem because there are several attacks on different layers, on physical layer, on MAC layer, on different protocol layers that lead to energy depletion. So you can, for example, wake up these devices every second and then you will drain the battery. That's one of the big problems. Then think of updating. You know the problems with maybe your smartphone. You will get updates, I don't know, every other night. There are every month operating system updates. But how do you do this if you have millions of devices? They're only really weakly connected. There's a wireless link. Maybe the link is only unidirectional. And you have millions of these devices installed somewhere. The life cycle, for example, in building automation is rather 30 years. 10 years operating time with a single battery. That's the idea. So how can you do updates? How can you trust the updates? Can everyone do updates? Or who's allowed to do the update? How do you really do it if you have millions of nodes? Do you propagate the updates somehow? How can you check the status of a single device? Unsolved problems. This is exactly where we do our research in. So how can you do something that's called remote attestation so that you can make sure that a certain wireless sensor node has a certain software? So that's big problems. That's completely unsolved. So and what we see today is that you have, yes, an internet of not really trustworthy things, because quite often also the companies manufacturing the devices, they just grab some protocols. Oh, there's a TCP and there's an IP and we put it all together and we add some whatever layers and it works. Yoo-hoo, let's sell it. Half a year later, updates, no one cares. And you see many of these devices, you cannot even update. And sometimes this is even a feature. The companies say, well, no one can do anything to the software, but how to update. So that's really a big issue. Okay, but this is not really a problem of the wireless communication or mobile devices. This is rather a problem of weak devices, and many of these devices. Okay, so this basically concludes mainly layer 3, because the main issues here are the routing and the problems of these different protocols. Okay, are there any questions to sensor networks? I know we could have a lecture only on sensor networks, Internet of Things, and in fact we have these lectures from time to time. Because then the next section covers layer 4. Well, basically there's not that much to say about layer 4, but there are problems. So, and the main problem is shown here. That you all know, for TCP we do something like this three-way handshake. We can already transmit some data with during this handshake, but we can also send a separate HTTP request, a response. So this is rather this transaction-oriented scheme if we use HTTP, access web pages. So that's what we do with our normal computers every day. But what happens if you have a wireless connection in between? And the example shown here is GPRS. And GPRS, you can easily have a delay of half a second, 200 milliseconds or more. So that means it takes quite a long time before you set up the connection and then transmit data. And especially the problem is TCP works with a lot of timers. If you don't know this, look up in computer networks. So TCP estimates the round trip time and sets many parameters based on the round trip time. So for example, timeouts. When should I complain about a missing acknowledgement? This is based on, for example, 2 times the estimated round trip time. But here the round trip time is quite high. That's a problem. The second problem is that TCP, developed 1974, so it's quite old, 46 years old, thinks if I do not get an acknowledgement, this is due to congestion. So a router inside the network dropped a packet. Because what else could happen? We have wires. So I transmit a packet, and if the packet is lost, this must be congestion. Here in the wireless area, we have transmission errors and we can roam between networks. So we might lose an IP packet due to interference, due to the handover. And this, by the way, is the reason why, for example, LTE offers this lossless handover. So we have severe performance degradation. Because if we lose a packet during handover, TCP thinks there's a congestion and then slows down data transmission. So the data rate goes down. So if the network like LTE offers, for example, lossless handover, this is perfect for TCP. If we use UDP, well, there's no retransmission, so we don't care. Then we can do something like this seamless handover I explained in the context of LTE, because UDP is quite often used together with voice over IP. And there it's more important that it's seamless. Then maybe we lose something, but we cannot tolerate delays. But you see, somehow a transport layer and this wireless transmission, the transmission doesn't really go together. So there are some problems. Okay, some more issues. I explained some solutions. Well, what a solution mean? This is more or less from research. So indirect TCP, snooping, mobile TCP, they exist as research projects. We can take some of the ideas, but they are not really implemented in your mobile phone or whatever. What we can use is, for example, fast retransmit, fast recovery. So that means that as soon as the sender gets some acknowledgements, at least the sender thinks, okay, the connection is not dead. Maybe we lost the packet, but as I receive acknowledgements, the can't be really a big congestion in the network. And we can use this by sending or retransmitting again acknowledgements after handover to signal the sender, oh, no problem, this is only a handover, but please continue sending with a high data rate. Otherwise the sender would assume congestion and the data rate will drop. So that's one of the ideas. Transmission timeout freezing, you can try this. So that basically means you freeze a connection, and this can be done by, for example, transmitting a receiving window of 0. So in TCP, as you hopefully know, the receiver can set a receiving window, and the receiving window tells the sender basically how much data, unacknowledged data, can I receive. So how large is my buffer at the receiver. Then we have something like selector-free transmission that's built into TCP. What never made it into products is the transaction-oriented TCP, so that you really can have transactions like you have in HTTP. So we live with our today's TCP and we can fine-tune it. That's basically the idea. And then I also showed you how can we improve the existing TCP. What is this fine-tuning? And you saw there are many recommendations. Sometimes I recommend really different things. So please use header compression or do not use header compression. Use timestamps, do not use timestamps. So it depends on the setting which optimization is better. But what the important thing was, not that you have to know exactly this formula, but that you think of this formula that the data rate we can achieve does not depend on the data rate of the link layer, but it depends on the maximum segment size. So this is how large can the segments, the packets, be on layer 4. So that's a fixed number. And so that means mainly it's round trip time and loss rate, loss probability. So loss probability, this depends on interference, but also on how good can we fix errors on this layer 2. So fixing errors using forward error correction or extremely fast repetition of the data on layer 2 between a mobile phone and the base station, for example. So then we can reduce the loss probability layer 4 experiences. And then extremely important, the round trip time. If the round trip time is high, you see from this inequation, this really limits our data rate. Because TCP derives from the round trip time many of its timers. How fast do we retransmit? When do we complain about missing acknowledgements, etc.? So that's really the main parameter influencing the performance of TCP. And now I hope you understand why in the newer generations of mobile phone systems, 4th, 5th and 6th generation, we'll talk about this in the next chapter. Well, one main concern is how can we really lower the round trip time? And this is mainly a problem of the wireless link, because there we have to do this forward error correction. So we have a so-called algorithmic overhead by calculating the redundancy, and this increases round trip time. So the delay between your mobile phone and the base station. So you see, in the end, well, we did not really change TCP. We did not go to a new TCP. Maybe a good idea, but large installed base. You have millions of computers using TCP and it has to be somehow compatible. To be honest, inside the mobile phone network, we use different protocols. I didn't cover here. This is also covered in computer networks. It's the stream control transmission protocol, SCTP, and some other protocols that are better suited for the jobs that have to be done in wireless networks. But end to end, we are talking with our mobile phones to normal servers. There we have to use TCP, for good or bad. So there are reasons for both positions. Let's change it completely, or let's stay with TCP. Okay, so as I said, you don't have to know the formulas, but what is the main problem if we use the classical TCP over wireless link? Why can there be a severe performance degradation? You should know the keywords here. So why can the data rate really drop extremely in TCP? It's congestion control, absolutely. So you should remember, congestion control in classical TCP assumes no acknowledgement within a certain time, for example 2 times the round trip time. So I send a packet, then I wait for a while, so you send a packet, and then you wait, and you expect within 2 times round trip time, I should receive the acknowledgement. If the acknowledgement is there, fine. If the acknowledgement, for example, does not arrive or arrives too late, you retransmit. And at the same time, you lower the data rate because you assume there's congestion. The problem here is, in wireless systems, you have a lot of interference. You may simply lose a packet because it's destroyed. Plus, we have mobility. That means we could have a handover from, let's say, a wireless LAN to an LTE system, or between different wireless LANs, or whatever, or fixed networks to wireless networks. And this may also cause packet loss. But there's no congestion. So why lowering the data rate? You should continue sending at the same high data rate. So congestion control is exactly the problem. But we cannot kick out congestion control because this TCP friendliness and congestion control and the way TCP behaves, it's quite often also called TCP friendliness, keeps the internet together. So that creates the stability that the internet works. So there's also a term called TCP fairness. We cover this all in computer networks, so that the protocols should behave in a friendly and a fair way. UDP doesn't do this, but TCP does it, and some other protocols also do it. Without being fair in the network, the internet would simply break, or you will have a lot of congestion. So the routers are quite important, so they drop some of the packets if we have congestion, but also the protocols are important. So this is why you cannot simply kick out TCP. Then I explained some of the enhancements. What are the problems and why they're not really widespread? So I showed you the table just seconds ago where I said, okay, we can use this and this, but all the others, no, not really used. That's always the same problem, why we do not really use these enhancements or similar problems. Yeah, the point is, if you use enhancements that change the behavior of the protocol or even the format of packets, etc., everyone has to implement it. Otherwise, it's not compatible. So that's one of the reasons. So you cannot simply go to a completely different system. And then there's also another reason that let's say if we look at maybe this one, if you have something in between, performance enhancing proxy, whatever it is, I talked about Snoop TCP and some other solutions. The problem is that you break the end-to-end semantics of TCP. So if it's encrypted, then you're lost in between anyway. So what can you do with encrypted connections? But also TCP works end-to-end. That's the idea of layer 4. And if you break this end-to-end semantics, many things do not really work in a proper way. So you can do this, but there might be some problems. So end-to-end semantics are really a problem, no matter what you do in between. And there are some solutions, but usually as soon as you use encrypted links, it doesn't work. And for many websites today, everything is encrypted. So use HTTPS, and then you cannot squeeze in between and break up the connection and use these performance enhancing proxies or whatever solutions in between. So that's one of the problems. Okay, and then what should you optimize then? So we cannot really kick out TCP. Yes, there are some other solutions, more on computer networks, but what could we optimize? What should the wireless systems really optimize so that TCP really works? There are two things, mainly two things you can. Loss probability, that's extremely important, and round trip time. So you should remember this. So RTT is important because TCP derives many timers from the RTT. And the loss probability, that's important because if you do not fix the problems immediately on layer 2, TCP thinks, oh, there's congestion. And then the data rate drops. So what you do quite often today is you, maybe misuse TCP a bit because you start with a large sending window and you transmit immediately all the data you have to transmit, for example, to access an HTTP server. And then you get the answer back, and that's it for the connection. So in the end, TCP can never stabilize, so you never have this kind of fairness, etc. So all the mechanisms cannot really be applied if you have this kind of short-living connections. And that's what we have, for example, for HTTP. And HTTP traffic is quite a big part of the traffic we have in the internet. And the other big part, video, there we use UDP. So TCP and wireless systems, yes, it works, but there could be better solutions. Okay. Are there any further questions related to internet protocols, wireless systems, mobility? So, if this is not the case, otherwise ask whatever you're interested in. Then that's it for layer 3 and layer 4.